increasing your afterload pressure as we age. So that's going to happen to everybody. So everybody's blood pressure is going to increase a little bit as we age. Just whether or not it'll increase enough to become problematic is the question. In my case, it probably will, because I'm starting out with mine being a little elevated already. Some of you, I was amazed at some of the blood pressures we had in there. I think we had some that were like 110 over 80, things like that. It was really good. Okay. Yeah, this general diagram, I think we went over this, the ways we can flow through a capillary bed. We know that capillary beds are those thin vessels that are between the arteries and the veins. We get through capillary beds pretty much one of three ways. We either bypass around it in an anastomosis or a thoroughfare channel, or we gotta flow through it. Okay. And if we flow through it, we go through the meta-arterioles, then into the capillaries. That's where nutrient exchange happens. And then we go into the venous side capillaries and into the veins. So we'll talk a little bit about these arteries. Oh, before I get too far. Remember how I mentioned in class that the only way you can tell the difference between an artery and a vein, well, not artery and vein, sorry, between the different classes of veins is their size. That's the point of this chart, is to break that down. Here we're talking about arteries. A big elastic artery, what we would call the conducting arteries, they have a diameter, in this case, of 1.5 centimeters. That's massive, okay? 1.5 centimeters, about like that. Okay, that's the lumen size of the aorta. That's huge, okay, for a blood vessel. You don't have many of those. Okay? You've got pretty much the aorta, the pulmonary trunk. The common carotids are a little elastic, the subclavian's a little elastic, but beyond that, then you're pretty much into muscular. So your muscular one, now here we've got a lot smaller, all right, half a centimeter, about half a centimeter, 6 millimeters in diameter. And then we get down to arterioles. Arterioles, they give you a diameter here of 37. Now I've seen different books refer to this, that's 37 micrometers, which would be 0.37 millimeters. So less than half of a millimeter is maximum. Now I've seen books that'll describe arterioles are going all the way up to 1 millimeter. Okay, so I'm not sure that's a fast and tight rule there. And what we'll see in a second is you'll have capillaries the same size as arterioles. So you'll have capillaries that go all the way up to, say, maybe 50 microns. And so the difference there is going to be in their tunica media. An arteriole will be the smallest vessel that has a tunica media. Now, let's go down here a little bit. Talk about different types of capillaries. So here's a picture of a generic capillary. You notice around the outside of the capillary here, there's no muscle. Okay, there's no muscle. If there was, then it would be an arteriole. So instead, what we have is just a simple squamous epithelial layer. So these are simple squamous cells. We call that endothelium, if you remember that. Epithelium that's on an inside layer is called endothelium. Okay? Now, like all epithelium, almost all epithelium, you've got the cell itself, and then you have this excreted or secreted glue-like material, which is the basement membrane. So most epithelium has a basement membrane. It's one of the characteristics of epithelium. And that's it for a capillary. You've got the simple squamous layer, the endothelial cell, and its basement membrane. And beyond that, you're just into the tissues that are around it, interstitial space, or whatever's out there. Do you remember the terms apical and basal surface? Do you remember those terms? Okay. Well, every epithelial cell is said to be what we call polar. And in this sense, it just means they have a top and a bottom. The apical surface is the free surface, the one that's not connected to other stuff. So in that case, that's the luminal surface. That's here. That's your apical surface of the epithelium. And then down here, where it's connected to the basement membrane and whatever tissue is outside of that, that's your basal surface. So for things to diffuse through an epithelial cell, they got to go through those two surfaces. To go through, they would either have to go from apical to basal, basal to apical. So then the basolateral surfaces, or just the lateral surfaces, are out here. They're the edges of the cells. Now I'm drawing your attention to that because something interesting can happen at these lateral borders. Right now we're showing those two epithelial cells touching, and then what they call a tight junction. I don't know if you remember what that is, but a tight junction is this thing where you've got protein bands connecting the cells. That's called the zonula adherens. And then you've got a waterproof filament thrown in there called the zonula occludens. And that's to make the cells stick together really tightly and to be waterproof. Okay? So you've got tight junctions here in these epithelial cells that do that. You can see why we'd want the cells to be waterproof, because we don't want stuff leaking out of our blood vessels. Except when we do. And that's the neat thing about blood vessels. We can change this. That connection will change depending on what type of chemicals we release. If we release things that increase what's called vascular permeability, these lateral surfaces actually loosen up. Okay? Pro-inflammatory compounds like histamine will do that. Okay? You release histamine into the bloodstream, one of the things it will do is it causes increases in vascular permeability. The lateral borders will loosen up and the capillaries become leakier. And we see the manifestation of this, right? You get a cold, you get sinusitis, and you get a lot of histamine released in there, and the nose becomes bright red, okay, because those capillaries have become leaky, and they're letting fluid leak out into that area, and that's what causes the swelling that you have in response to an inflammatory response. The redness is just due to increased blood flow in the area. Well, that's going to have some important connotations when we get to immunity later on. If you're trying to fight an infection, you'll want more fluid going to that area, because it's going to bring more nutrients and more disease-fighting white blood cells. And that's great in a small area. What if it happens throughout your entire circulatory system? If your entire circulatory system all of a sudden becomes leaky, you can't maintain your blood pressure. Okay? And we call that toxic shock when that happens, or septic shock. If you get some kind of systemic infection, the real danger is that you release so many pro-inflammatory compounds that your vascular system loses its integrity, the fluid just seeps out of the vessels, and you can't maintain blood pressure. And that's actually what kills you in something like toxic shock. Okay, so that's that lateral surface, and we'll talk about some of the connections that we have there. This capillary that we're showing right here would be a continuous capillary, meaning that those lateral borders don't have gaps, and the cells themselves don't have holes in them. Okay? It's continuous. The inside lining is continuous without breaks. This would be what you would have in a thoroughfare channel, for instance, as blood tries to flow from one side of the capillary network to the other side without really leaking out or anything. That's where you're going to find continuous capillaries. Continuous capillaries are supply lines. They're going to bring blood to an area, but they don't do a whole lot of exchange. Okay. Anything else? So as it says here, some capillaries are more permeable than others. Well, okay. Here we go ahead to another slide. This one is 19.3. I keep forgetting to call the tech people and ask them why my screen is cut off. Here. Anyway, take a look at this and then bounce back here and look at that. What's different? We'll do like the optometrist. A, B. Okay. What is it?
Bigger gaps.
Bigger gaps. Permeability, I heard. Yeah. Okay, so if you look here within the squamous cell, the endothelial cell, look at these little thin spots, those holes. There's nothing like that here. Okay. And you're right, the lateral borders might be a little looser, but it's really these holes that we're looking at right here. Well, that's kind of taking our continuous capillary and making it more like a colander now. Now it has little holes in it. Those holes are called fenestra. Okay. Little holes are called fenestra. I forget which book I read it in years ago, but I guess that's Greek for window. Okay, so it means a little thin window. You can have fenestra that have an intact plasma membrane or one without it. If it has an intact plasma membrane, it's called a fenestra with a diaphragm. And if there's no plasma membrane at all, then it is literally a hole in the cell, and that's just called an open fenestra, or one without a diaphragm. All right. Now, where endothelial cells are located, you have to keep in mind that endothelial cells do a couple of things. They make a smooth lining for blood vessels so that we have nice laminar flow. That's one of their functions. Make a nice smooth flow surface, low friction. Another thing is they actually secrete chemicals that suppress clotting. Endothelial cells make chemicals called prostaglandins prostacyclins that suppress clotting. Okay, so they release chemicals that suppress clotting. Another thing they do is they act as a filtration membrane, which means that anything that's going to get from the blood into the tissues has to go through them. And any waste product that goes from the tissues into the blood has to go through them too. So they have a big role to play in selectivity of what can go in and out. Okay? So what do you think is more leaky? A continuous capillary like this or a fenestrated capillary like that? The fenestrated capillaries. Which one do you think is more selective? A fenestrated capillary without a diaphragm or a fenestrated capillary with a diaphragm? Which one's more selective? The one with the diaphragm, right? Okay. So where do you find fenestrated capillaries? Well, they give you a few ideas down here. They mentioned down here the kidney and the small intestine. Okay? In your small intestine, you're doing massive amounts of nutrient absorption. Continuous capillaries wouldn't be able to keep up with that rate. So fenestrated capillaries can absorb a lot more. The kidneys, also a place where we do hyperfiltration. And we'll talk, yeah, this is AP2. We'll talk in some of the upcoming units. Mondays and Wednesdays I teach AP1 and AP2, so my head's kind of like, which one am I doing? We'll talk about renal function, and we'll talk a lot about what's called the filtration membrane, which is the beginning of a nephron. And it's kind of built like a colander. And it has fenestrated capillaries and some other specialized cells that are very, very picky about what they let in and out. Okay? So anywhere you have a lot of filtration, we'd expect to see that maybe also, well, in the stomach, the gastric capillaries, things like the spleen, some in the liver. I'm trying to think where else. And really, anytime you'd be coursing through something like a muscle, where you have a lot of nutrient exchange there as well. There's a third type, this guy. Now this guy looks like a fenestrated capillary that got beat up, okay? It has these big gaps at its lateral borders. I think you can clearly see that, okay? These big gaps. Well, those gaps are called sinuses, okay? And they have large fenestra without diaphragms, but they have these gaps at their lateral borders called sinuses. So these are called sinusoidal capillaries. They're usually the largest of the capillaries, so they've got a big lumen, and they're very, very leaky. Now there's a trade-off. The leakier you are, the less selective you are. Okay? So the most selective capillaries are going to be your continuous capillaries. The least selective are going to be the sinusoidal capillaries. You're going to find sinusoidal capillaries where you have to do really rapid exchange, and you're going to sacrifice the selectivity for that. So places where you're going to find this would be things like the spleen and lymph nodes and the liver. Okay, we have to do a lot of very rapid nutrient, not necessarily nutrient, but metabolite exchange. And the sacrifice is selectivity. We don't have as much control over what comes in and out in those areas. Liver, spleen, bone marrow. Bone marrow is very similar to lymph nodes in that structure. Now let's go back to this picture. So now here we have an arterial coming down and an arterial branch going into a capillary network. Slide is 19.4. We go through the capillary network or capillary bed, and then we go into the venule and small vein and so on. Nothing confusing about that, right? Okay. We know this passageway going right through the middle. We might label that as a what? Well, so that one goes through the capillary bed, so that wouldn't be an anastomosis, but it's the right idea. This one's the thoroughfare channel. That's a thoroughfare channel. An anastomosis would be if, say, a vessel like this came and went around the capillary bed and connected over there. That'd be an anastomosis. All right. Then these little guys are meta-arterioles. Here, there, there, there. These are going to feed into the capillary network. And look, they got that chewing gum structure around there. That's smooth muscle. Just a few cells of smooth muscle around that. We know that's a precapillary sphincter. Okay. So if the tissue, sometimes I'll just ask you, what would be in these white spaces, guys? Is it empty space? What would really be here? In the white space is blood?
Oh, I'm sorry. I thought we were talking about
Tissue, right. Whatever organ this capillary bed is feeding, that's what would be out here. This might be skeletal muscle tissue. It might be cardiac muscle tissue. It might be renal tissue. Who knows? But it's whatever the organ is. Okay, that's what's out here. All right. So if this organ is currently not having oxidative stress, or O2 debt, meaning it's metabolizing at a rate higher than its oxygen supply, then it's happy. It's happy, and it's not releasing chemicals to encourage vasodilation. Under those conditions, these are going to be constricted, or at least slightly constricted. So they're restricting blood flow because this organ doesn't need more blood flow. Now, if this organ gets starved, it's going to start releasing things like a lot of excess carbon dioxide and things like creatinine and nitric oxide. And some of these chemicals will actually cause vasodilation, and they'll cause these blood vessels to dilate by making those sphincters relax. That's called the autoregulatory mechanism. That's what allows